Hi, it's Miss Barnhart, and today let's take a look at the chi-squared test as a statistical tool that we can use to analyze the results of genetic crosses. You may be asking, what's chi-squared? In genetics, we can predict the genotypes based on the probability using our Punnett squares. The Punnett squares give us our expected results. The chi-squared is a form of statistical analysis used to compare the observed results we get from our laboratory investigations with the expected results to test the validity of the results. In other words, how close is close enough? Note, chi-squared is the name of the variable. You're never going to take the square root of chi-squared, or you're never going to solve for chi. You're going to be solving for chi-squared using this formula. If the observed and expected values are the same, then the chi-squared value would be 0. If the chi-squared value is 0 or small, then the data is fitting our hypothesis very well, because the expected values would kind of match. So if we calculate the chi-square value, we can determine if there's a statistically significant difference between what we expect from the Punnett square and what we observe in lab. First, we're going to calculate chi-squared. And the first step is to determine exactly what the expected and observed values are. Observe is easy. That's our data. We just write down what we get in lab. The expected values are what we think we should get based on probability, the Punnett square. We make a null hypothesis, which will always be the observed values are not significantly different from the expected values. Any differences we get are due solely to chance and not some other factor. So the strategy to do this easily is to make a table that has the expected and actual values, and then make columns that we can fill in the intermediate values to calculate chi-square. So let's take a look at an example. If we cross 2 pea plants with yellow cotyledons, and we ended up with 58 yellow cotyledon plants and 29 green cotyledon plants. If we had the hypothesis that the plants were heterozygous, then 3/4 should be yellow and 1/4 should be green. And I get this from doing a basic Punnett square. So to do the math with a population of 87, that's 65.25 yellow cotyledon plants and 21.75 green plants. Now, you have a reference table, and it's got the formula for chi-squared, and it's got what the values mean, that O is the observed individuals, E is the expected number of individuals, and sigma is the sum of the values, in this case the difference, squared, divided by the number expected. So it's sigma O minus E squared divided by E. What you're going to want to do is to make a table. And you're going to set up this table with columns for O, E, O minus E squared, and O minus E squared divided by E. And I recommend you practice this because this is going to be something that you get the formula, but you're not going to get the table written for you. So notice, if I have 58 yellow and 29 green, that's a total of 87 plants. That's in the O column, the observed column. Now my expected column, I have 87 total plants. I multiply by the fraction that I get from my Punnett square, which is 3/4. So 3/4 times 87 is 65.25. 1/4 times 87 is 21.75. And I want to add up the totals of both to see they're both observed and expected, or 87. So I know I haven't done anything kind of weird here. The next thing to do is to find the difference, the O minus E. It really doesn't matter if you have the positive and negative numbers because it's going to go away with the squares. The square term in the next one, but O minus E is 7.25 in both cases, the negative 7.25 for the green. Now I take my difference and I square them and get 52.56. And the next step is to take that difference squared and divide by the expected value. Be really careful that you divide by the expected value. Notice I get 0.81 and 2.42. And this is going to give me a chi-square term when I sum those two together of 3.43. And that's my chi-squared term, and that's the term that I'm going to use to compare to see whether or not my results are statistically different from my expected results. Okay, the next step is to determine the degrees of freedom, and that's just simply the number of categories minus 1. So for example problem, we have 2 categories, green and yellow. So we have 2 minus 1 degrees of freedom, or 1 degree of freedom. Now I'm going to have a table that's going to give me my probability values and my degrees of freedom. The p-value is the probability that the differences are due to chance. And the higher the p-value, the higher the probability that the differences are due to chance. In biology, I'm looking for a p-value of greater or equal to 0.05, so 5%, and that's the standard value. So I'm going to use the degrees of freedom and determine the critical value at p equals 0.05 on the table. So I've got 1 degree of freedom, and I've got the probability of 0.05. So you'll see the critical value is 3.84. So when I compare my chi-squared term, if my chi-squared term is less than that critical value, then that means the probability I'm getting is greater than 5% that the results are due to chance, and that's the value I'm looking for. Some tables are going to have probability values of different values than 0.05. So unless you're told to use something other than 0.05 as your p-value, always use p is equal to 0.05 when you're determining what the critical value is. Now for my conclusion, what I want to do is compare that chi-squared term to my critical value. If the chi-squared term is greater than the critical value, then that means that there's a statistically significant difference between the actual and expected values. So the difference is not likely due to chance, it's due to probably something else. So I reject the null hypothesis, and the data is not supporting the mode of inheritance that I hypothesized. If the chi-squared term is less than the critical value, then there is not a statistically significant difference between the actual and the expected values. So the differences I'm seeing are likely due to chance. And I don't reject the null hypothesis because the data does support the mode of inheritance that I hypothesized. So I hope you see that this chi-squared tool, this chi-squared test, is yet a statistical tool that you can use to see if the results that you get from experimentation are close enough to what you hypothesized from the Punnett square. If the chi-squared value is less than the critical value, you're good. I hope that's helpful.